In this video, what is a solution? We're going to think about reactions that occur in water. And what does it mean for a reaction to occur in water, and what information can we learn about that? So, a reaction that occurs in solution is something called an aqueous reaction. So, aqueous means in water, it means dissolved in waters. So, we know based on our real lives that we can dissolve lots of things in water. You can think about any powder that you add to water, stir, and then it's fully dissolved. We can also think about things that you add to water and maybe they don't fully dissolve. If you add salt into water and you stir it, it fully dissolves. If you add sugar to water, cold water, it doesn't always dissolve. So we know that there are things that change how much something dissolves. And if instead of salt or sugar you added rocks, the rocks aren't going to dissolve. So we know that there is a spectrum between something that fully dissolves, something that partially dissolves, and something that doesn't dissolve. So what does that mean? So one type of thing that we can see in a water reaction or an aqueous reaction is something that completely dissolves into its ions. So what that means is things like NaCl is going to dissolve into Na plus aqueous plus Cl minus, also aqueous. We could see the same thing with magnesium nitrate, where that would dissolve as well. So the next thing is a non-electrolyte. A non-electrolyte does not dissolve into its ions. Now, I want to be clear, this doesn't mean that it doesn't dissolve. You can no longer see a solid. So some examples of that are things like sugar. So if we have C6H12O6, when you put it in water, we see the same thing, C6H12O6. Or if you add ethane or ethanol, so C2H5OH, stays as C2H5OH. So the difference between an electrolyte and a non-electrolyte is whether or not it turns into its ion. Now, we talked about an electrolyte and a non-electrolyte, but there is in fact a third option where something only partially dissolves. So a weak electrolyte is one that partially dissolves into its ions. And so these are things like weak acids, so acetic acid, which is CH3COOH, only partially dissolves, which is why we see these unique arrows, into H plus CH3COO minus. And so what these arrows mean that I'm going to highlight in yellow right here, that means that it goes both ways. Whereas the ones highlighted in blue, here and here, those only go in one direction. Well, for the non-electrolyte, it doesn't do anything. But for sodium chloride, when it dissolves into its ions, it doesn't come back together. So we can see the differences between all of these. So let's see, what else can we learn? So we know that something can go into solution, but what we don't know is what that looks like. So let's think about what it means to be dissolved. We can have something that is soluble, and so this is that it completely dissolves into its ions. And so we can think about soluble as things that when you add them to water, they completely dissolve. Now, you can have soluble and insoluble non-electrolytes, but for the purposes of this, we're really thinking about electrolytes, things that dissolve into their ions. So they are soluble or insoluble, and this does not dissolve. So it's not just that it does not dissolve into its ions. it becomes a solid. So in another video in this series, we are going to talk about what does it mean to be insoluble and how can we use that information. So if we have something that can dissolve into its ions and something that can't, we want to be able to think about what does that solution mean. So when we think about this, there are two essential parts of an aqueous solution, the solvent and the solute. The solvent is the substance that does the dissolving. So in this case, it would be more like the water or whatever liquid you have that you are adding the solute to. So this is the substance that dissolves. So you can think of the solvent as water and the solute as a solid that you add. In this case, in order for this to really work, it needs to dissolve into solution. So one of the reasons that ions dissolve in water is due to the polarity of water. So what does it mean for something to be polar? Polar means that it's going to contain something called a dipole moment. A dipole moment. And so a dipole moment means that one side is negatively charged and one side is positively charged, but only partially. So while we haven't learned how to draw the structure of water, the structure of water has an oxygen, two hydrogens, and two lone pairs. And it turns out that along this axis, we see partial charges, which gives us a delta minus and a delta plus. A delta minus and a delta plus basically say the hydrogens are slightly positive and the oxygen is slightly negative. This interaction is going to be what allows ions to be stable in water. The dipole moment of water is a unique property. This property is essential for how biological systems work. It is essential for how all of the other components work as well. And so one thing that is interesting is when we have a solution where we're going to have a negatively or a positively charged ion. In this case, I'm going to make a blue ion, which will be positive. What we're going to see is that the water molecules will orient themselves with the delta minus surrounding the negative charge. However, if we were to have the opposite charge, so in this case, I'm going to have a negatively charged ion, the water molecules would orient themselves in the opposite direction. Where the delta pluses surround the negative ion. So what we will see, if you look at the graphics that I provided for you, what you'll see is structures of ions fully surrounded by water. This property of water is going to allow the ions to be stabilized in solution. It isn't just that the ions fall apart, it's that they are stabilized by the water and that the water molecules surrounding them allow for the charges to be displaced. So now that we have a substance that's been dissolved into the water, we actually need a way how we can think about that chemically. Previously, we've talked about density, which is how many grams per volume. But we could think about doing that with solutions. But it's kind of hard to think about, okay, did you make it this density solution? Did I make something different? What we want as scientists is the ability to say, I'm going to recreate what another scientist did exactly. And we're going to be able to do that by determining the molarity. So molarity is the amount of solute in moles divided by the volume of solution in liters. Or we could think about it a little bit more like this, where big M, which stands for molarity, so this big M here is a unit, means molarity, is just the moles of the solute divided by the liters of solvent. And so we can use that, and I use that in my research lab to say, we have a 0.75 molar solution, which means no matter how much of that solution you take, you're going to get the same component. So let's think about an example here. If 0.75 moles of sodium chloride is dissolved in 1 liter of water, what is the concentration in molar? So we're going to take our moles, so M equals moles over liter. Oops. And so we're going to take our 0.75 moles, divide that by 1 liter. And in this case, I'm going to get 0.75 molar. So provided we can determine the moles and we have a volume, we can determine the molarity or the concentration for any type of solution. So let's look at a few more examples. So what is the concentration in molar for a 1.75 liter solution with 25.5 grams of KBr dissolved in it? Now we have learned in previous videos how to go from grams to moles. So we are going to continue to use that skill. So we're going to take our 25.5 grams of KBr. I'm going to divide that by the molar mass, which is just the sum of the mass of potassium plus the mass of bromine, which in this case is 119.00 grams in 1 mole. So that's going to give me 0.214 moles of KBr. So the molarity is moles, which is 0.214 moles, divided by the volume, which is in the problem of 1.75 liters. And in this case, we are going to get 0.122 molar KBr. And if we check the problem, we will see that we have the right number of significant figures. So if we can determine the moles, we can determine the concentration, provided we have a volume. So let's look at a second example. So what is the concentration of a solution in molar? What is the concentration of a solution in molar? We'll just scratch those words out. Created when 23.4 grams of sodium sulfate is dissolved in 125 mils. So again, we're going to be able to convert to moles and we have a volume. So we're going to take our 23.4 grams of sodium sulfate, divide that by the molar mass, which is 142.05 grams in 1 mole. It's going to give me 0.165 moles of Na2SO4. So the molarity is moles divided by liters, but our volume is at 125 mils. So we're going to take our 125 mils, we are going to divide by 1,000 in 1 liter, and that gives us 0.125 liters. So from here, we're going to divide the moles divided by the liters. So 0.165 moles divided by 0.125 liters, and that gives us a 1.32 molar solution that also has this correct number of significant figures. So the ability to calculate molarity is essential, but the next step to this is the ability to use molarity in calculations. So we can use the molarity of a solution. And so the molarity, as a reminder, is moles in 1 liter. So the amount of moles, if you have a solution of 1.1 molar, that equals 1.1 moles of your sample in 1 liter. And so we can always take the units back apart if they're in molar. So we want to be able to determine the volume or the moles that are in a portion of this solution. More often, we don't make a liter of something. We make 100 milliliters or 300 milliliters or something else. So this asks how many moles of sodium sulfate are found in 50 milliliters of a 1.25 mole solution, or 1.25 molar. So now I want to know, if I measure out 50 milliliters, how many moles are in there? So in this case, we are going to take the volume. We're going to convert that into liters. So I'm going to take 50 milliliters, divide by 1,000. and that's going to give me 0.050 liters. So now I'm going to take my 0.050 liters, and I'm going to use the molarity as a unit conversion to convert from liters to moles. So we know that there's 1.25 moles in 1 liter, and that gives me 0.0625 moles of sodium sulfate. Now what I did is I took the molarity and I split apart the units and I canceled out the liters here in order to convert from liters into moles. This is very similar to how we've used density in calculations. So let's look at a few other examples. I would like to create 1.55 liters of 0.758 molar sucrose solution. How many grams of sucrose should I use? So I need to figure out how many grams of sucrose would give me this molarity in this volume. So I'm going to take my 0.758 moles in 1 liter. I'm going to multiply that by the concentration or the volume that I want, 1.55 liters. So this gives me the moles. And then I'm going to convert using 1 mole, which is equal to 342.34 grams of sucrose. And that gives me 402 grams. So what I did is I took the molarity, multiplied by the liter. This gave me a unit of moles. And then I canceled out the moles to get grams. This is quite similar to other calculations we've previously done. So next, if the reaction requires 0.0123 moles of nanospheres, how many milliliters of the 0.321 molar nanosphere solution should I utilize? So in this case, we're going to use the moles of 0.0123 moles. And I need to use the molarity in order to determine how many milliliters. So let's figure out how many liters. So I'm going to flip the molarity, basically divide by that value. This allows me to get rid of the moles divided by the liters. Now I'm going to multiply by 1,000 milliliters because the question asks for that. And I find out that I need 38.3 milliliters. This gives you the correct volume. So molarity is the moles divided by liters, and we can use that in a manner very similar to how density is created.